All right, let's go ahead and get started. I do want to welcome to this worksheet. This is Colligative Properties Calculations. This will be part one. We're going to divide this one into two separate parts to try to give ourselves a little bit better chance of understanding this just by slowing down just a little bit. You are going to need a calculator and a periodic table for this, so if you don't have those handy, go ahead and pause the video and we will get started. So here we go, colligative property calculations. Let's start with a definition. What do we mean by colligative properties? Well, colligative properties are properties that change based upon solute being dissolved in solvent. All right. So they include such things as vapor pressure, and that's what we're going to focus on in this first half of the worksheet, and freezing point and boiling point. And we'll take a look at those in the second half. So colligative properties are properties that change based on solutes being dissolved in the solvent. Well, what do we mean by that? Well, let's take a situation. Let's say, for example, that we have this. Let's just say that we have water. So I'll draw a container, and I have water in this container just like that, right? So the little dots that I'm drawing, the little blue dots, are meant to denote the water molecules, right? But we also know that in this container, that some of those little blue dots are going to vaporize, right? They're in the equilibrium between liquid and gas, or liquid and vapor, and they're going to vaporize. And so they'll be present as vapor particles above this liquid water, right? And those particles are going to exert a force on the size of the container, and we'll learn in our gases units in a couple of weeks that means a pressure is going to be exerted. We call that pressure the vapor pressure. We call that pressure the vapor pressure. But what happens if we add to that some contaminants? And by contaminants, I mean could be salt, could be anything, right? So we add to that, the little red dots mean that we've added something to the water. That's going to change the vapor pressure. It's going to decrease the vapor pressure. And what we want to focus on now is how much is it going to decrease that vapor pressure. All right, so let's look at number one. Number one says this. It says the vapor pressure of water is 23.76 torr. Now that's pure water, and we're at 25 degrees Celsius. So 23.76 torr, and torr is a unit of pressure. The vapor pressure is 23.76 torr at 25 degrees Celsius, right? So just keep in mind that torr is a unit of pressure, 23.76 is for pure water, and we're at 25 degrees. Here's what it says. Calculate the vapor pressure of a solution of 7.50 grams of formamide, that's HCONH2, in 1.50 times 10 squared grams of water. So we're going to add formamide to the water. It's no longer a pure water solution. It's now formamide and water. All right. So we're going to use a particular law, and it is called Raoult's law. And Raoult's law says this. Raoult's law, and this is for one volatile liquid, right? Volatile liquid, remember, means one that evaporates readily, is this right here. P sub A is equal to chi sub A, and I'll explain what that is in just a moment, times P sub A naught, okay? And I'll explain all these right now. Where P sub A is the vapor pressure of the solvent. So that means when you've added whatever you're going to add, what's the new vapor pressure? That's what P sub A is. Chi sub A is the mole fraction of the solvent, all right? And P sub A naught is the vapor pressure of the pure liquid. Now, we've been given that information in this problem. So let's proceed. The first thing we're going to need to know is we're going to need to know the moles of water and the moles of formamide. So let's do that first. We've got 1.50 times 10 squared grams of water times 1 mole of water per 18.02 grams of water. I just divide this, right? Just got this from the periodic table, just added up 2 hydrogens and 1 oxygen, and I get this number, 8.32 moles of water. So now I know the number of moles of water, and now I need to do the same thing for formamide. I've got 7.50 grams of formamide over 1 times 1 mole per 45.05 grams of formamide is equal to, and we get this number considerably smaller. But we expect that We expect the solute to be much smaller than the solvent. We have 0.166 moles of HCONH2. That's the solvent. Oh, excuse me, the solute, right? So now we've got the two. We've got water, and we've got the solute dissolved in the water, which is the formamide. Let's determine the total mass. Just add the two up. 8.32 times 0.166 moles is equal to a total of 8.49 moles. That's for the solution of formamide in water. Now let's determine the mole fraction of water. Remember, this is the mole fraction of the water, not the formamide, because water is the solvent, right? So moles of water divided by total moles is equal to the number of moles of water, which is 8.32 moles of water, divided by 8.49 moles total is equal to 8.980. So that's chi sub A. So 98% then of the solution is water, right? P sub A naught, we've been told, is 23.76 torr. Remember, torr is a unit of pressure. So the new vapor pressure, the pressure after the formamide has been added then, is this right here. P sub A is equal to 0.980. That was calculated. That's chi sub A. That's the mole fraction of water times the pressure, the vapor pressure of the pure water is 23.76 torr. When we multiply these two together, we get 23.28 torr. The vapor pressure of the water is now diminished, slightly, but diminished by the presence of the formamide. 23.28 is the new vapor pressure of the water with the formamide now introduced into it. That's number one. Let's go on to number two. Number two says this. What is the vapor pressure? Let's see if we can... There we go. What is the vapor pressure of a mixture of 0.30 moles of acetone and 0.50 moles of methanol at 25 degrees? The vapor pressure of acetone is at 25 degrees is 345 torr, and the vapor pressure of methanol at 25 degrees is 295. So what we want to know is, what is the vapor pressure of this mixture? All right. So this is not just something dissolved in water now. This is two different volatile liquids. So we're going to use a variation of Raoult's law that has to do with two volatile liquids in this case. So for example, this is it. P total, the pressure total, the vapor pressure total of the two liquids is equal to the pressure, the vapor pressure of the first one times its mole fraction plus the vapor pressure of the second one times its mole fraction. So I'll just read, where P total is the vapor pressure of the mixture, P1 and P2 are the vapor pressures of the pure liquids, and chi1 and chi2 are the mole fractions of the two liquids. So the first thing we're going to need to know is the total number of moles. So we've got, for the first one, 0.30 moles. We're told that in the problem. And for the second one, the methanol, we've got 0.50 moles. So the total number of moles is 0.80 moles. So P1, we're told, is 345 torr, right? So the pressure of the vapor pressure of the acetone is 345 torr. Now, what we're going to do now is we're going to determine the mole fraction of the acetone. Well, the mole fraction of the acetone is the number of moles of acetone divided by the total number of moles. And that's going to be 0.30 moles divided by 0.80 moles. So now we've got P1 and we've got chi1. Now let's turn our attention to P2. P2, we're told, is 295 torr. 295 torr. And chi2 is the number of moles of methanol divided by the total number of moles. So that would be 0.50 moles of methanol divided by a total of 0.80 moles. That mole fraction then is 0.63 moles, and we've got chi2 now. So now let's use Raoult's law for two volatile liquids. Here we go. Here's what it says. P total is equal to 345 torr. That was the vapor pressure of the first substance, times 0.38, its mole fraction, plus 295 torr times its mole fraction of 0.63, and that's going to give us 130 plus 190. The total pressure then is the total vapor pressure is going to be 320 torr. That'll do it for this part of the worksheet. I'll see you on the next one. Thanks. Bye-bye.